Hi there, my name is Aaron Chan, and welcome to my introduction on how to set up a static structural simulation for a cantilever beam in ANSYS. In order to follow along with this material, you will require an ANSYS Workbench license, which is typically offered to Purdue students under the ANSYS student license. You will need to download the ANSYS Workbench application. You will also need a computer capable of running ANSYS, and you will also need a computer model of a cantilever beam if you want to directly follow along with this tutorial. A link to the model of the cantilever beam will be included in the description of this video. To start, we want to use ANSYS static structural as engineers, since typically we want to predict the stresses and the deformation in a structure. Now, what does static and static structural mean? In this case, static can mean either that the object is not moving or that it is not moving relative to uh, a larger structure, which it might be the smaller structure is attached to. So in this case, we are analyzing a cantilever beam. Some examples of cantilever beams might be a diving board or maybe a balcony on an apartment. And so we can use static structural in ANSYS as a simulation tool to predict how these different structures will behave in the real world before we actually start to build it, which helps us to save time and money that might have gone into building a real world structure. But at the end of the day, it's important to remember that ANSYS static structural is a simulation. And so it's not to be taken as a 100% representative of the real world. So I guess to start off our tutorial, we first need to drag and drop the static structural block into the project schematic. We can do this by going under Toolbox and underneath Analysis Systems. We can go down near the bottom and drag and drop static structural into the project schematic. Here we can see that static structural has 7 cells. The first one states that it's static structural. The second one is engineering data, and this contains information on various materials that we might use in our simulation. In this case, this is predetermined data, and so we don't need to worry about this cell. Under geometry, we can include the cantilever beam geometry into our simulation by right-clicking the cell, and under import geometry, you can either browse for the model geometry in File Explorer, or since I've opened the file earlier, I can click beam.stp to import the geometry into ANSYS. Once that geometry is imported, I can double-click Model to open up ANSYS Mechanical, which is where the static structural simulation will actually take place. You can also open up ANSYS Mechanical by right-clicking and selecting Edit. Now, it may take a couple minutes when you first open up ANSYS Mechanical. So for the sake of time, I've already preloaded ANSYS Mechanical. But this is what it should look like when you first open up ANSYS Mechanical. So you can see here, we have our cantilever beam model, and we can tell as well that is we are using the ANSYS student license since it says student in the top right corner. So on the left-hand side here, underneath project, we have geometry imports and geometry, where we can see the beam that we imported. Now under materials, we have structural steel. And so this is the default material applied to an object in ANSYS. If we would like to import or assign another material to the beam in our example, we can first click on materials, right click, and go to insert material assignment. And so first we need to select a geometry to assign the material to. So by coming to the top middle of the screen, we can select body or hit Control B to change our selection filter to select the whole body. Otherwise, we might select something like a face, which would only assign a material to the face. And so we would like to select the whole geometry, the whole body, and then going to geometry in the bottom left. By hitting no selection, we have the option to now apply the material. And so hitting apply, we can see that the beam turns red, which means we have successfully scoped the geometry or selected the correct geometry. Now going back to the bottom left, under details of material assignment, we can go to material name underneath definition. This cell is also highlighted in yellow. We can click on this cell, and then here we have an arrow pointing to the right. By clicking this arrow, we should be able to see different materials. And typically, what will happen is we are able to select a new material and assign that material. But in this case, we will continue to use structural steel for our simulation. So continuing to use structural steel, we can move down again and we can see coordinate systems. In this case, we won't need to use this feature for our simulation, but this can be helpful for orienting different meshes or orienting different forces so that we can get it in a specific coordinate system. Now, if we go down one more step, we can see mesh. In this case, mesh will create a mesh which consists of elements and nodes. Elements are made up of nodes, and nodes are points where a mesh or elements are able to interact with one another. And so a node is where essentially forces and different characteristics that we apply to the beam will be transferred. And so in ANSYS, we are able to automatically generate a mesh without first applying a specific property. So by hitting right-clicking mesh and hitting generate mesh, we can automatically create a mesh. Here we have a nice looking mesh, and typically when you create a mesh, you want it to be uniform, and as we can see here, it is uniform. If we would like to create a finer mesh, we can go to hit mesh and then down by sizing, under defaults, by element size, we can define an element size. Since our beam is 0.15 by 0.15 meters in width and height, by typing in 0.15 and then going up to mesh again to regenerate the mesh, we can see that a single element right here will make up the width and height of the beam. But going back down to element size in the bottom left and typing in 0.05 and then regenerating that mesh, we once again get three elements through the thickness of the beam. Now that we've created the mesh, we can move on to static structural. So by selecting static structural, we can now insert a force and apply a boundary condition to our beam. So first, we can right-click static structural and go to insert, and right next to insert, we can apply a fixed support. Essentially, a fixed support results in the beam not moving and not deforming at the face or boundary where the fixed support is applied. So for simulation's sake, we will apply the fixed support to the left side of the beam. Once I've selected the beam using the face geometry filter, I can go down to the bottom left and hit apply. And so now that the fixed support has been applied to the geometry, I can go back to static structural, right-click static structural, go to insert, and go to force. By selecting force and selecting the face opposite to the fixed boundary condition, I can reselect the face geometry filter and select the face that I am interested in. By once again hitting apply in the bottom left corner, I can apply a force to that face. Now, I also need to define the amount of force applied to the beam. So for the sake of this simulation, I want to apply a 1000 Newton force downwards to the face. And so I can go to define by and either double click or select the drop down arrow and hit components. And since in this case, downwards would be negative y, I can go to y component and type in negative 1000. And we see that the arrow is pointing in the direction I want, which is downwards. And so we know that we are successful in implementing the force. So now that my fixed support and force have been applied, I am ready to solve the simulation. When I solve the simulation, I'm interested in different things like stresses and deformation. Now, when I right-click solution, I can go to insert, deformation, total, and click that option to insert the solution information. Essentially, what solution information is it gives me information on, it gives me a quantitative information on how the beam performs. And so in this case, deformation tells me how much the beam moves relative to the fixed support when the force is applied. Essentially, it tells me how much the beam will change shape. Now, if I go back to solution and I right-click it and go to insert and go to stress and then go to equivalent von Mises, I can insert the equivalent stress that the beam will experience. We are interested in stress since stress is how, I guess, we determine if the beam will break. More stress will typically result in more deformation, and typically we can predict the stress, the point at which a material or structure will yield or break by seeing if the stress that is experienced is less than or equal to the yield strength of a beam. And so now that we have imported the deformation and stress solution information, to actually finally solve the simulation, we can go back up to static structural, right-click it, and hit solve. Now, depending on your computer, this can take anywhere from a couple seconds to several minutes. In the bottom left hand of the screen, we can see the progress bar, but now that the solution has finished running, we can see on the left-hand side that there are check marks next to all the boxes. So we know that our simulation was successful. So looking underneath solution, we can see total deformation and equivalent stress that we inserted. So by clicking on total deformation, we can see that the beam is deforming. We see that the side where the fixed support was applied has zero deformation, but the side opposite to it has the maximum deformation. And we see this color gradient going from left to right, from blue to red, and that helps us visualize the deformation of the beam. Now, if we go back to the left-hand side, we can select equivalent stress, and this tells us the stress in the beam. So we can see that as the beam goes farther from where the force was applied towards the fixed boundary condition, we see the stresses greatly increase. Now we can tell that our simulation was at least successful since this makes sense in engineering. From an understanding of structural mechanics, we know that the farther we are from a force, the greater the moment or torque that the beam will experience internally. And so it makes sense that the greatest amount of stress occurs on the left-hand side, where the fixed support is, or farthest from where the force is applied. Now, typically, we can also use hand calculations or analytical methods to calculate the stress in a cantilever beam. We can do this to validate our results and have, I guess, another way of checking that our results are right. In this case, we won't do this for the video. However, since we have collected our total deformation and equivalent stress information, we are now done with the tutorial. Thank you for listening, and I hope you were able to learn how to use ANSYS through this tutorial. Thank you.